All right, we are back, ladies and gentlemen. The HiFi Summit Day 3. We are here with Ken from KCC Scientific. How are you doing, Ken?
I'm all right. How are you guys?
We're good, man.
Doing well, Ken.
All right, that's great. So I'm very appreciative that you guys would take the time to put something like this together, making it so easy for us to enjoy this funny situation we're in right now. And indeed, we're also very appreciative of those who are joining us, and we hope you enjoy this and have a little bit of fun. So is there any other information you want to share with the audience about how we manage this process?
Well,
Nope.
not really. They're
Not really.
aware of how it all works. Why don't you just introduce yourself? What do you do? What are some of your products? Just get into it.
Absolutely. Oh, all right. So, okay, Ken Reindel. I've been doing some form of R&D and product development for the course of something like about, 40 years or so, truth be told. And KCC Scientific is our focus here today. Our purpose is to solve very difficult mains power problems, and we've done so with a series of what we call mains reconstruction units. They're also excellent frequency converters for people who are trying to use something out of its country of origin. And it could be a turntable, or it could be a stereo system, amplifier, preamplifier, whatever it might happen to be. We take care of those problems with our products, and people love our stuff because it gives them the ability to use things that they thought they'd never be able to use, or bought something in the wrong country and said, oh, we'll just plug it in here and we use a cable adapter and everything will be fine. Well, guess what? It doesn't quite go that easily when there's a 60 hertz versus 50 hertz issue. So we're happy to be able to step in and service folks. Today, what we're going to do, though, is we're going to step aside and talk a little bit about the evolution of powering audio. And some of you who've are somewhat familiar with some of the issues you have with power and managing power in audio systems know that there are these devices called power conditioning. There's regeneration. There's DC mitigation products that take out the DC. All these sorts of things that have been around and solve problems of various degrees. And we're going to compare. We're going to first go do a quick definition of what the problems are we're trying to solve, and we'll see here our what we are going to cover today. And we're going to kind of try to keep this light and fun and fast, but at the same time, if we're welcoming questions, and we'll stop a few times for questions. So we're going to start by talking about mains frequency amplitude waveform issues, power factor distortion, and then those are the problems. Those are the issues we're trying to deal with. And then we're going to jump in and talk about some of the things that have been around for a while and some of the new things that are out there now to help kind of cure some of those issues. Among those are power conditioners, DC mitigation, regenerators, and so forth and so on. And then we're going to wrap it all up at the end and continue at that point to answer questions. So here's our, let's define our problems. And starting with mains frequency stability. Well, it's interesting that if you look at the history of the power line frequency across the world, it's absolutely crazy. There was a time when 16.66 hertz was used, anything from that to 133 hertz. Throughout Europe, there was no standard for years. Great Britain had something like 10 different frequencies, whereas 50 hertz wasn't adopted till much later. In the United States, we kind of started out a little bit earlier with, in the 1920s with 60 hertz, and the primary driver there was the fact that 60 hertz looked better to us with lighting, but secondarily it makes transformers a little bit lighter and smaller and a little bit low cost. So interestingly enough, in Japan, half the country was 60 hertz and the other half was 50 hertz. Well, guess what? It's still that way today, of all things. Who would have guessed? In North America, much of California stayed at around 50 hertz until 1948. So you can imagine what a mess all that made for folks who were building things that depended upon the line frequency for speed, like clocks and even turntables. Even early turntables had this issue. So, and by the way, still do. So in the US, there's this thing called time error correction that was established very early. And the reason it got established was because believe it or not, because of clocks, because electric clocks were the new technology, and they wanted to be able to use the mains power line to manage the time of all the clocks that were on it. So Henry Warren developed this really cool gadget, and we talk a lot more about this in a presentation, the presentation we did for Rocky Mountain Audio last year, and anyone who wants to go back and review some of that, it's kind of cool stuff. So the system by which the mains frequency in the US and elsewhere in the world, how that's managed, is an incredibly complex electromechanical system with multiple loops, servos, very complex things with huge generators. When those generators get loaded, they slow down. Then you got to speed them back up, but you don't want to overload them by driving them too hard, on and on and on. It's a complex process. The result of it is it's very difficult to keep the frequency constant. And we audio folks want that frequency constant because our turntables depend upon the speed of the frequency. And so here, for example, I took this data last year, and I bet you if I sat down and took this data this year, it wouldn't be any different. It would be very similar. Peak to peak speed would change 0.35% as a result of this frequency variation right here in this lab. And so this data is pretty typical versus what we see elsewhere in the world too. And Terry always kids around with me and says, maybe this is why we sell so many products to Great Britain. Look at their frequency. Look at their frequency variation. It's pretty substantially worse than it is elsewhere. So it's kind of interesting. And you can look at these other various countries as well, and you'll see that everybody's got the same problem. This is a difficult thing to control, and we just have to kind of manage it with the consideration that it's about a 1% variation that we're going to see in speed of our turntables if we rely on the mains power line to take care of things for us. And it's not going to get a whole lot better. In fact, they're even looking at now discontinuing time error correction for a variety of reasons. And we talked more about that in last year's, summit as well. So you can jump back there if you're interested. The issue with turntables, it affects the speed. It's a direct proportion. When the frequency drops, the turntable speed drops, and vice versa. So we've got to do something about that. So that's one issue. Let's go on to mains amplitude and waveform issues. So everybody's familiar with this one. Everybody knows about over voltage, under voltage. But how many of you think about the fact that as it's changing, it could cause DC bias drift in amps and preamps? Well, it actually can. And you could have a power amp that's pulling heavy current. And, one of our engineers actually measured he was running a very high power amplifier and was able to see his voltage on his line in that room drop down below 105 volts from 123. So that's a heck of a lot of variance. That suggests a whole lot more, line resistance there in the house wiring than maybe you might expect. And when you think about it, some folks say, well, just run a special line to your system. Well, that's not always possible. In fact, quite a few of our customers come back to us and say, we live in an apartment. We can't change it. We can't put in a dedicated. We'd love to put in a dedicated line, but we just can't. It's just not an option. And by the way, the electrician wants to charge us $3,000. Well, all right. Well, there's reasons to look at other ways to solve that problem. There's still plenty of energy there, even though that voltage has dropped. So there's a lot to work with. The question is, how do we do it? So what about lightning strikes? Well, everybody says the same thing. This is nothing new. Lightning is literally unstoppable. If you get a direct hit on your house, I don't know what you're going to be able to do to prevent damage. It's just how it works. You could try lightning rods, all the surge protection you can get, isolation and more isolation. But if you get a direct hit, you're going to be in trouble, and there's no way around that. So the problem with amplitude issues is that it takes electronics to mitigate them. And so we look at things like power conditioners, surge protectors. We talk about regenerators and things like that. But even with these things, you're not going to stop serious surges. You're not going to regulate frequency, and you're not going to get isolation out of any of the methods that are mentioned above. But let's focus more on that later on. We're going to get to that and some of the details. As far as mains waveform purity is concerned, does anybody know what this might be? Anybody want to guess? Well, I know nobody wants to guess right now because we have
Go
a
ahead,
lot to go
Shauna.
through. Oh, we have someone who wants to guess.
mean,
All right, great.
it looks like a sine wave that doesn't have any like rounded off like bottom parts. But
Yeah.
other than that, I
Other than
don't
that,
know.
pretty darn distorted sine wave. Well, guess what?
Yeah.
Where that was measured? That was measured right at my living room outlet with everything turned off.
Oh
So
wow.
that's the power I'm getting
Okay.
into my house, and I don't think that it's a whole lot different anywhere else in the country at this point. Why is it so bad? Well, there's this thing called power factor correction that we're going to talk about. There's a lot of old non-power factor corrected equipment out there that just basically chops the top right off the waveform. And for decades and decades and decades, this stuff was built this way. And so now, of course, there's folks and standards trying to be set to clean this up, but it's going to be a long time before this gets fixed. Another thing that does it is heavy appliances and motors. They dump tons of harmonics on the line, and that kind of messes up the power factor as well. And by the way, they can also contribute to DC offsets. So let's talk a little bit about this power. What the heck is it anyway? It sounds weird, strange term, but we don't generally hear around the house. Well, what power factor relates to is how the voltage and current are related to each other, and how they are consumed in an electronic device, and how much distortion an electronic device dumps back onto the line in the meantime. If the load or the device you were powering was purely linear and resistive, then they'd be related by Ohm's law, as you see in that nice little picture there to the left, where yellow is the voltage and green is the current. And they're right there with each other, inverted, but right there with each other. And what happens, though, is that when you have equipment that distorts the mains current because of the way it loads it, now you have this problem with power factor. And a little dirty secret that nobody wants to realize is that our audio equipment actually does contribute to that problem too. And let's look at what, for example, that's all about. Well, in most traditional quote unquote linear audio power supplies, which by the way are actually technically considered non-linear loads, bet you didn't know that, did you? You thought your amplifier was linear. Well, maybe not as much as you might think. Here's the mains plug, here's a power transformer, and this is the rectifier diodes that turn this AC here into DC here. And these large filter capacitors that everybody's just completely obsessed with, and rightfully so. I mean, they do serve their purpose, but the result of all that is this. Here's our incoming voltage waveform, this yellow, and here's the current that we're drawing off of our line. So all of that 100 feet of Romex in our walls that goes down to our main breaker box, okay, that is seeing this current. So, is it at least a possibility that this could be creating noise somewhere, this current? Well, everybody looks at the voltage waveform and how pure it is and never looks any further. But if you actually look at the current, you realize what a mess is being made of our environment with this kind of current, these kind of current spikes and the harmonics that they generate, and where else they get into magnetically. So this is a real issue. And you could see the equation here for power factor is, basically here's the relationship between the voltage and current, that's the angle, and this is the total harmonic distortion of that current. So as this distortion goes up, power factor goes down. Ideally, 1 is what you want. 1 means it's linear. As you get away from 1, that means you have more total harmonic distortion on that line, and it's gonna present itself as noise, and it's getting it in places that you don't want it. So what do we do about all this? Well, I mean, the voltage purity, as I said, seems to be less of an issue in the current waveform because obviously no one wants to talk about it, but it is an issue. Regenerators can clean up the voltage waveform and make them look beautiful, but they can actually magnify the current distortion issues and create more harmonics. Feed your box in your house. So is there a way that we can clean this up? Well, we're getting there. We've got a few other things we got to talk about first. Let's start by talking about power conditioners now. We want to try to do a cleanup. The most obvious thing we do is we go out and buy a power conditioner. Well, what's a power conditioner anyway? Well, its primary function is filtering. That's what it does. Its secondary function is over voltage and surge protection. And most of these things, if you look at them, that's what they've got. They're nice enough to build these as secondary functions, in which we also want to do something about those too, those issues. And kind of a third function is you'll find some of these things, many of these things they add outlets. So now we have a bunch of outlets that we can use too, as you can see here, this in the PS Audio Dectic, which is one example. All right, and then some of them have voltage displays, as you can see to the right here, and even battery backup in some cases. Some manufacturers that you run into, Furman, Panamax, Nortex on the budget side, Pile Pro, and PS Audio is one of the better ones, apparently. I didn't realize Panamax actually sells a special high current surge outlet, which is kind of a cool idea. Actually, you can buy these from Home Depot, but I'm not sure that they're rated for quite the same level as these Panamaxes are. So, there's, as with most equipment, there's varying degrees of what they can do to help you. So how do these things work overall? Well, we're going to dive into that just a little bit to folks' appreciation. Now, one of the things I learned kind of doing a little research for this presentation or this program today was, there are a lot of DIYers out there. And DIYers, we're interested in helping those folks because that's how later on folks become audiophiles or perhaps, engineers or whatever it might be. So we want to give folks kind of a little bit of direction and advice on these things. And safety is the absolute number one thing you want to do. You want to really pay attention to what you're doing to keep yourself safe. Now, we have a lot more to cover, but before we do, can we maybe stop and take a few questions? Because I know we've covered a lot so far.
Absolutely. Go ahead and come back over here. If there's any of them that you see in the chat, are you able to see them over there on the right?
I'm not seeing them right now, so I have to.
I got you. You've got your screen on there.
Yeah.
Your
Maybe I
PowerPoint.
can take it down.
That maybe just minimize that. You should be able to see all four of us, and then over on your right, you'll see questions, and we'll go through some of these as well. And so, if you guys got any questions, go ahead and feel free to drop those in the chat. Make it easier to find.
Yeah.
Put those up there for Ken.
One thing I hate are dirty sine waves. We do not want any dirty sine waves. So do you think the little power outlet things actually do a lot to minimize all that?
Well, actually, that's going to be what we're going to dive into here now.
Okay. Because those are the products that really interest me, because I got a lot of stuff that I got to plug in here in my music studio, from synthesizers to summing boxes and all kinds, and studio monitors and stuff. And like, I don't want to buy like 10 like power conditioners. If I can get something in the wall plugs and just change out the 4 wall plugs, boom, I'm set.
Okay, so I guess
at least today, none of those wall outlet devices are going to do a darn thing for the distortion of that waveform.
Gotcha.
Sorry about that. It's just not possible. Not today. Maybe
just an idea.
Yeah.
So I have a quick question. So, you're showing us all these measurements. How would that translate to what the end user might hear in his or her system at the end of the day? Like, what difference would I notice with and without?
Well, it all depends upon the piece of equipment you're powering and how sensitive that equipment is and how it processes that power waveform. As you saw in that diagram, most audio equipment that's on the higher end of the scale uses huge transformers and rectifiers and capacitors and conducts only on the peaks. So for the most part, that bad waveform is only going to limit how much power you're able to output from an amplifier at the peaks. So as far as how much noise it picks up, that's going to depend upon how the engineers laid out the equipment and how close those windings are to other things. And man, it's just really hard to predict it exactly until you plug it in.
So it varies based on the device itself. But let's just say generally, let's say worst case scenario, I have this amplifier. So I'm not using any analog, no turntable, all digital. And what would you say I might be able to experience as far as the difference?
Let me just tell you what people tell me. what they tell me is they hear a difference in the baseline, the background hiss and noise, and they hear differences in hum. Those are the two big things that we hear kind of quite a bit. Now, some of that, though, and we're going to get into this, it's not all that simple. It's not all caused by the distortion in that waveform. Some of it's caused by system ground loops and pickup, like you saw, for example, the distortion in the current that I described as flowing back through that 100 feet of wire. That could be radiated back into a piece of equipment and cause, again, some sort of harmonic noise, hum, something along those lines too. I mean, that's pretty obvious that's a serious issue. When you get 5 to 20 times the current that your RMS should be drawing, that's a lot of energy being dumped into the environment, into the air, if you will, as magnetic interference.
So we've got a handful of questions that have just come in at the bottom over here on the right. So let's take a look at a couple of these if you're okay with that. All right, how about this one? How does the end user measure these waveforms without high-end equipment? Is that possible?
Well, it's hard, but there's actually, yesterday, and I'm going to talk about this, a fellow in one of the presentations talked about a cool little device. You guys know it. You guys saw it. That you can actually plug in and you can hear the noise on the power line with this thing. I'll describe it a little bit more. I brought it up along with the reference to the particular session. That's one way to do it. But beyond that, it's tough. Other than listening to, then you hear problems like noise in your background or whatever, and you try a piece of equipment to see what the difference is. And until you do that, it's really going to be tough to tell if that piece of equipment is going to help you or not. That's one of the but this cool little gadget, I thought, was a neat way to get a little bit of insight into that issue. So you might, when we get to that, it's something to consider.
Okay. Let's see. What about maybe this one? This is pretty technical here. What is the difference between the changes in the wall numbers versus what really comes out if a well-regulated power supply on a properly designed product? Maybe on a properly designed product.
Oh, really, really good question. A really well-designed regulated power supply will probably, I mean, in theory, could be designed so you never saw any of that issue come through. But chances are it would probably have to have built into it things like those filters and the DC mitigation and the other things that we're going to talk about in order to be able to fully benefit from that. And the other question is, there's quite a bit of difference of an opinion on how to build a piece of audio equipment. Name a piece of audio equipment, whether it's a preamp, a power amp, whatever it might be. There's tons of disagreement on what the best approach is. And one set of engineers, one company, I know yesterday we watched Macintosh's presentation. They're going to have a particular way they think it needs to be done, and somebody else is going to have their preference. And some of those things trade off the performance of noise rejection. So it's just really tough to come up with a single design that everyone agrees on that's going to solve all the problems. And that's where, folks are out there looking for ways to make the power better going into their equipment, so that regardless of what decisions the engineer made, look at this, you got good performance.
Gotcha. Cool deal.
All right. Okay, you want to jump back in?
Yep, let's do it.
Let's see here. Get back to this thing. Can you see me?
Yes, you're good to go.
Okay, good. All right, so I just wanted to take you through a couple of these things and share some insights as to what's going on inside these boxes. This is a filter. This is a Furman AC215A filter. Not a bad little piece of equipment. It's fairly miniature. As you can see inside, they've gone through extremes to keep things tight and keep this product small, which is a good thing. Here we have the power coming in, and if you look here, it's distributed down to the board where there's a little circuit that basically acts to sense over voltage on the line. And if that over voltage should occur, it turns on this red LED and shuts off this relay, which disconnects your stuff over here from the incoming line. Very clever little circuit. and it usually stays on until you do something to reduce that over voltage. Now, you might think to yourself, there's no way I'm ever going to get an over voltage of 137 or 140 or 145 volts on my power line. You know what? I'm going to tell you something. A few years ago, we bought this house, and one of the first few months we were here, we had a failure in our mains breaker box. And what happened was we lost the neutral. And as a result, everything that was on the other side of that line was damaged. We had a computer power supply blow up. Thankfully, no audio equipment plugged into it. We had lights burned out. It's phenomenal how much when you have an unbalanced load and you lose a neutral, that you could end up with some pretty serious problems. And this product would have prevented damage to that computer had it been in series with it. So there is value to having a circuit like that in there. Here is a device called an MOV, which is used to prevent, if a lightning strike happened a few streets away and an impulse, a 3,000 volt impulse came across, this thing would probably clamp it and keep your device safe. This is a common mode filter element. It's wound with, it's a toroidal core with special magnetic properties, lossy properties, wound with a fairly thick gauge wire, which hopefully doesn't provide too much series resistance. And then if you look over here, interestingly enough, there's these, first of all, these capacitors that are used as, they're called X capacitors, and we'll show you in a second where those are. And then this circuit here, interestingly enough, looks like it just might be a DC mitigation circuit. Now, I don't know that, but it sure looks a lot like it to me. So very interesting. And of course, a circuit breaker here, which is a good idea, that prevents catastrophic things. When catastrophic things happen, it prevents them from, getting out. Like if this MOV were to fail somehow, it would prevent that from becoming a serious issue for your house wiring. So kind of a cool little device. Looks pretty well built. This is kind of the circuit, and really quickly, this is the common mode filler we just described, and these are series mode fillers that they do different things. This usually is good for RF. This is usually good for lower frequencies. Here's your X capacitors and your Y capacitors, very important devices. We'll talk about those real quickly. Here's the MOV, which is across the line with a fuse, of course. Never have an MOV without a fuse. And its purpose is to prevent over voltage spikes from getting through. Filler capacitors are safety rated. These are important devices. Never build a filter, for all you DIYers out there. Never build a filler without using X grade capacitors and Y grade capacitors. They're rated to go across the line and fail safe. And they're rated for way more voltage, hopefully, than you'll ever see, but they can accommodate the effects of an MLV. In other words, it gives their MOV room to work. So, okay, so let's jump ahead here now. So what could go wrong with this using one of these devices? Well, one of the biggest issues is matching the device that you're buying to the piece of audio equipment that you're using it with. And frankly, it's a crapshoot. You just don't know until you try it. Generally, the folks who design these filter boxes are thinking about these things, and they're trying different equipment, but there's no guarantee that your device is going to look the same as theirs did. So the other question that always comes up is, does series impedance affect sound quality if it's in the power line? Well, that's a very highly debated issue, and I am not going to try to challenge anybody who believes that it is an effect. I've seen it cause problems, and with house wiring today as it is, and 14 gauge being the prominent gauge that's used, yeah, it could actually be audible. So there's no question there that there's something to consider. Also, if you're going to build something, be aware. Look at the parts. They don't behave ideally. Here's an example of a super not so ideal part. It's called a capacitor. It's called on the right here and in the top right graph, you can see it's a ceramic capacitor that it's a 16 volt capacitor that at 10 volts is already down to half its value. So these things get overlooked a lot by folks that are very knowledgeable and know how to design equipment. So you obviously have to keep your mind on understanding every part you're planning on building in there if you're going to do DIY. Here's that thing that we talked about a few minutes ago that might be kind of cute towards helping track down noise. And check out MoFi's 10 free tips that was on yesterday at around, I don't know, around noon sometime. Even Joe can guide us on that. But this device was really cool. He was actually able to plug it in and hear the noise that his Apple power supply was injecting onto the line. Actually, I might get myself one just to see what this thing does and how well it works. Some other additional technologies. Sometimes folks come up with really clever ideas. This is a cool one. It's by Taurus Power, and it's an audio isolation transformer that also regulates voltage. It uses 16 taps on a transformer and switches that connect different taps depending upon what the line voltage is doing. So this top right device here is the Taurus Power. This one on the bottom is a Bryston. Honestly, I think they're made by Taurus. They're both the same. I'm not 100% sure about that, but when I was reading the Bryston description, it talked about Taurus. So it looks like they just might be the same one or share the same guts. Oh, one important point I want to make. If you think you need to isolate for whatever reason, for ground loops or whatever, please, please, please avoid budget import transformers. They are 4x underrated, and we actually have an entire blog on our site that describes this problem from starting with a customer who actually was experiencing a very strange phenomenon with one of those transformers, and we explained to them what was going on based upon what we've learned over the years of how these import transformers are designed. So be aware. Okay, so let's talk a little bit about superimposed DC and how it's mitigated. This was one that comes up periodically, and it's a real important one. So the first question is, we're talking about AC line here. Where in the world is DC coming from? We're not batteries in series with our power line, hopefully. So what's going on? Well, I'll tell you what, it's more common than you might think. And it's caused when any device that's plugged in somewhere on that line or even in the same locale where it's the device that's being plugged in is presenting an asymmetrical load. In other words, one half of the sine wave is loaded more than the other half. And it's not that hard to run across this. There are heat guns and shrink guns and hair dryers that do a weird thing. They add a rectifier in series with the heating element to basically drop the power by a factor of 4 because you're chopping off half the waveform. So some, but not all. I'll tell you, I've run across some really good, well-designed triac controlled speed controllers that work great. Some do, some don't. Blocked rotor startup current on appliances is a big source of this. Transient loads like big things like hair dryers, clothes dryers, even incandescent, high power incandescent lights are large banks nowadays with homes being so well lit. And if you're using incandescent lights, hopefully you're moving more towards the LEDs. But if you're not, you're going to probably see issues with this. And oh, by the way, not all LED and fluorescent lights are created equally. Some of them use rather low-cost power supplies, which also create issues. So what we did here, we just created a little, in the left here, we created a simulation, and out of this simulation, we put a rectifier there and loaded the V1, which is basically the power plug of your outlet. We loaded it with basically one of these devices electronically, and we created this waveform to give you an idea of what actually happens. And you can see the top peaks are chopped off, the bottom peaks are not chopped off. Well, that's going to give you a DC offset. So what? Who cares? So there's a DC offset. Why am I even worried about this? Well, it turns out that both toroidal and laminated E-core style transformers hate DC. They absolutely hate it. And even a few hundred milliamps of DC current causes the magnetic flux in the core to walk off into saturation. And you will hear it like you would never believe. And not only is it audible, but it's not healthy for the power supply, and it could blow fuses. I actually have a demonstration of this very effect. It turns out I own 2 of these fancy little devices, these little hot air guns that create this problem. And I'm going to demonstrate for you here. I have a rather large transformer that's used in one of our devices. It's a toroid, and I have a power supply. I can't see it here, but it's a power supply from the lab that has a laminated core like the one on the right. And I'm about to turn on this heat gun and show you what that actually does. Now, we ran this before, and apparently it is audible on here, so hopefully you'll hear it too. Here goes. I don't know if you heard that or not. I'll try it again. All I did was turn this thing on low, and you could hear the transformer inside of this power supply going absolutely berserk. So the interesting thing is that the toroid's also doing it, but it's quieter. And what happens with the toroid is after I shut off that heat gun, the toroid just keeps right on resonating for several seconds. So if you've heard your equipment within your stereos doing this, you know that you may have DC on the line, or somebody is using something around you that is doing this. Well, there's actually ways to mitigate this, and there's several devices out there that do this. This is by no means inclusive, but these were the ones that I was able to find. Emotiva, Van Alstyne, Humdinger, some equipment actually, literally, we just talked about this in the case of the Furman, actually builds this in. There's a lot of folks on the DIY sites talking about this. Please be careful. These are tricky devices to build. And some of the more clever common mode fillers and surge arresters, multiple outlets all come along with these things. So folks are finding ways to kind of integrate and group these functions together in these nice little boxes. And somebody was complaining on one of the sites, one of the blogs, that these things are like $300. And let me tell you, if you have DC driving your transformers and your devices crazy, it's a cheap price to pay to get that problem solved. So the way these things generally work is real simple. They take the input, they put a capacitor in series with it, as you can see here. The capacitors are generally tend to be somewhat large, but that varies. The more important thing is these capacitors have to be selected for low ESR, which is equivalent series resistance. That's a really important factor with these things. So if you're not familiar with these various elements, don't try to build one of these things yourself, because it probably won't work. The interesting thing about these things is the better ones will have current ratings that are higher, but I have not found one that has really high current ratings, like above 10 amps. So unless somebody knows of one, these things are generally great for equipment that's lower power. Higher power stuff, I don't know what you're going to do with this. So the diodes are in there, by the way, more than anything else, to protect the capacitor. This is an AC coupling circuit. That's all it is. The diodes protect the capacitor. So what can go wrong with these? Well, if the offsets are too big, with this heat gun, I was actually able to generate 3 volts DC on the line. I built a little circuit where I could measure it. And sure enough, 3 volts. Well, that wouldn't help. Those devices wouldn't help this situation, because 3 volts is well above the 1.2 that's in there with the diode. The diode clamp kind of keeps the voltage across the capacitor from getting any bigger than 1.2 volts, which interferes dramatically with the function of the thing. So it would probably help, don't get me wrong, but it wouldn't eliminate it. So the other thing that can go wrong is transients. The capacitor takes time to charge, so you're still going to get a little magnet. And as I said, these transformers, once they get magnetized with this DC, it takes them a little while to dissipate it off. So you might actually still hear it even with the device if the values of the DC go up and go away even instantaneously. So another thing with these is they don't really affect the mains frequency or help that in any way. And then we have the topic of regenerators. And everyone knows, I think everyone knows PS Audio for their regenerators. I couldn't find any other examples of a regenerator out there except for the PS Audio. Seems like a cool device, corrects for mains waveform aberrations and distortion, and it can eliminate DC offsets, and it will lower the output impedance of the mains as your equipment sees it once you plug into it. Seems like a lot of power in a relatively small device. So, if they're doing this linearly, there is no way they're reconstructing this mains from scratch, because you would heat your room with the thing if they did. So this is actually what we found as to how these work. And although PS Audio is our neighbor here, we don't really have any access inside their building. So we have to look up their performance, their capabilities, just like everybody else does through the patent office. And this is how these things appear to work. You have the input come in, It goes through an amplifier, literally through an amplifier that's bootstrapped to the line. And that amplifier acts as a correction circuit that takes out the distortion and the DC and all those other nasty things. And by the way, they also have a pretty robust filter on the input to this thing to knock out that as well. I don't know if they have a DC correction circuit on their power supply transformer. Who knows? But the bottom line is, it's a great idea, great circuit, but you know what? It doesn't do a darn thing for frequency at all, because this is just basically a tracker circuit that gives you what you put in. What comes out is what you put in, but it subtracts off the errors and the distortion and the DC and those sorts of things. And that's how they make that circuit work. Does anybody want to ask any questions right now before we go further? Or should we finish this section first?
Why don't we finish this section? We're getting closer to our time limit, but
okay.
But yeah,
you can do a Q&A, a whole Q&A section. I'm sure people have questions.
Okay.
Yeah.
So what could go wrong with these? Well, bottom line with these, they're great products, but they don't do anything for frequency. They actually could make the harmonic problem on the line worse because they lower the impedance and make the current peaks higher. So that's what you got to kind of consider with these. Now we have mains reconstruction as kind of the final thing here. So what is mains reconstruction? Well, what we do with mains reconstruction is we start literally from scratch. We take the input line, we turn it into DC, and then from there we go back to AC again. So we completely reconstruct the power line. With that, we can get frequency drift that's very high precision, 0.0002%. It's a whole lot better than a percent, obviously. We clearly will eliminate DC offsets and noise. In fact, this product will eat DC for lunch. It loves DC. It'll operate off of DC all day and night, and you'll never see a millivolt of that DC come out the other end of it. It completely eliminates waveform distortion, regulates voltage, and all the cool things that we need while maintaining good power factor. Very important. And it also provides full, if you wanted to, we can give you a mode to get out of that, but we provide full isolation. Remember that massive transformer? This is actually inside the product. So you get the idea. That's what you're seeing there when you look down on this snapshot in the photo there on the slide. So yeah, that's a workout. That's a 20-pound lift right there. So basically how this works is, as I said, it's a mains filter and power factor corrected converter, takes that DC, puts it into a DC to AC amplifier, isolates it, looks at what's going on in the output, provides feedback and corrects it, and that's it. That's simple, but it has a huge number of benefits as a result of it. And here's a couple of products that you see here in the picture that we offer that are lower power products, 100, 200 watts. Our Athena is 40 watts. These products come in super handy for people trying to power lower power things. Turntables where frequency stability is needed, where you need isolation. We get lots of compliments from folks where we've broken ground loops that they couldn't break any other way. So they really do a good job of providing power to your audio equipment without the downsides of some of the other methods we talked about. And just as an input-output comparison, sorry it's more than an outlet there, my friends, but this is what's coming in on the left, mains input, and here's what's coming out of our products. This is an example of our 500 watt unit running at full power. So pretty darn clean coming out of there. So if you compare the benefits of these basic techniques we've talked about now, kind of as a summary, the first column is filters, and you go across here, there's various methods. Filters kind of stack up at the end. If you look at all the different things we're trying to do to help us with power line issues, for a couple $100, you get a couple of things fixed. As you move to the right, again, the same thing. You get a couple of things fixed for a few $100. Regeneration fixes more things for somewhere between $3,000 to $10,000. And on the far right is the MRU approach, which honestly I think is the best deal. Is for $2,500 with a Mercury Audio, you can fix everything and then some. So kind of something to think about. So conclusions here, it looks to us like mains reconstruction may be the optimal way to revolutionize audio power moving forward for all the reasons we just talked about. And yes, we have solved countless problems. And every year that goes by, we solve more problems for folks all over the world, including in areas outside of audio. Folks are actually buying our stuff for medical grade applications, medical product testing. We get resounding feedback on things that we've been able to solve in the area of audio, hum, turntable speed problems, wrong local frequency and or voltage, and a myriad of others. So, we're pretty proud of the things we're able to offer, and we're happy to help folks who have questions or run across issues like this that they can't solve any other way. Or maybe they don't know that there's a solution out there like what we provide that can take care of these things. So hit me with the questions, folks.
Hey, Ken, great seminar. We've definitely got a couple of questions that came in. Let me pull a couple of these up here for you.
Oh, I got a random quick question. Is this a turntable speed situation specifically for belt-driven turntables, or does this affect direct drive as well?
What really matters is the type of motor that's used. Okay. And many turntables, you would be surprised. I know I was quite surprised at how many turntables even today use synchronous motors. And there were times when we heard about DC quartz driven and so forth, and those are great approaches, but it doesn't seem like that's the majority of the high-end turntables. There's some, but not all, so you have to beware. And with a simple product like our Athena, which I have here, this simple product will completely clean up everything you'd ever want to clean up with frequency, noise, et cetera, and so forth, and relatively inexpensive and affordable.
Cool.
And it does the job for folks on turntables. And I don't know of a turntable yet that product can't power.
Got a question, 240 volts.
Oh yeah, there's one down at, I've got about 3 questions on here. We'll go through. That's one of them. So here's a question for you. Understand from maintenance point of view, but how much can one appreciate the difference from a soundstage perspective? Any tests made to demonstrate the difference in a home theater?
Well, to tell you the truth, I can't speak from experience on that one. I don't know. I have a product right now from a customer with a home theater situation where he wants the product and it's going to be shipped to him this week, but we don't know the result of that yet. So he would be our first home theater.
Gotcha.
My guess is that it's going to help him, because it's what it's going to do is if you have multiple amplifiers in the system, it's going to provide a degree of isolation between those amps. So depending upon how he goes about configuring his system, he could get some benefits from this.
Cool. Here's another question.
Good point.
Right here from Steve. Can distortion from the mains be measured on the DC power rail of the audio equipment?
Steve, if the equipment is designed properly, the distortion on the mains is not going to be the thing that turns into distortion on the output, except that if your voltage is dropping dramatically as a result of that 100 feet of Romex in your walls, you will probably be able to hear the difference. Mm-hmm. Because when you start to drop the voltage, everything in your system is going to see that voltage drop, is going to react to it in some way. It's unquestionable. When you see 20 volts of drop on your line, you are going to see and hear differences.
Gotcha. And Patelgo, you have one for 240 volts.
All of our products are designed to do both 115 and 230. So yes, the answer is absolutely. They're worldwide and they're completely universal. You can plug them in anywhere and they give you either voltage and either frequency, 50 or 60 hertz.
Here's one from John.
Yes, I've heard of people using battery backups. Yes, I've heard of that too. And if it all depends upon the design of the system. I personally don't know of any battery backed up units that use isolation transformers and that do that the same form of regulation that we do, but maybe they work. It certainly is. I've seen them too. I've heard about them, but I don't have any data on how well they work.
I think I need to get a battery backup because I just got an email from Edison and we've been having high winds all last night and all today. So they might shut off my power. Just so anybody knows that there may not be an after party. I might not even be in the stream for the rest of the afternoon. It says we might shut off your power this afternoon.
Oh, wow.
Thanks,
Well,
Edison.
they're predicting storms here too.
Yeah.
We all
So
have
annoying.
that problem.
You got it. So any thoughts on connecting amplifiers and subwoofers into these types of power conditioning products?
I think our new Mercury products would handle a great number of power amplifiers and subwoofers, absolutely, without a doubt.
Very cool. Well, we're gonna have to jump out and start this new stream pretty soon, Shauna.
Well, if
Yeah.
anyone has any other questions, please feel free to email us, or we have an 800 number. You can use that. Give us a call, and we'd be happy to answer any other questions.
Great
Thanks,
deal.
Ken.
Ken, appreciate it, man.
Thank you so much, Ken. Everyone, this was Ken from KCC Scientific. And hold on for just about 10 minutes. We're going to get Sonus Faber in the mix here. So don't forget about jumping into the lobby discussion or the group video chat until that time comes. Our journey to the top continues. HiFi Summit Day 3. Oh, yeah.
Okay.
Hi, Terry.
Folks,
Bye.
take care. She's here.